right, so we are starting section 7.5, which is about work. And work with a constant force, A, that's supposed to be an A, constant force is just a constant force, we'll call it F over a distance D is pretty simple. W equals F times D, so force times distance. So in your example 1 in the text, they just say, okay, you have this box here and it weighs 50 pounds. You're going to raise it up 4 feet. And so the work done is W equals 50 pounds times 4 feet. So that's 200 foot-pounds. Okay, there you go. Pretty straightforward. Now, what turns this into a calculus problem is, what if the force changes as you go? And so just to change this a little bit, suppose, as we move to a height of 4 feet, a height h, the force is actually 50 minus 10h. So see, when h is 0, right, f of, oops, I'm not sure what I hit here, that, hit the text thing, f of 0 is that 50 pounds, but by the time you get to 4 feet, f of 4, that's just 50 minus 10 times 4, or whatever that is, 10 pounds. So it keeps getting lighter. Well, so how could we estimate how much work was done? Okay, well, pretty simple. We break it up. And, we could first start breaking it at, 0 feet, 1 foot, 2 feet, 3 feet, and then to get all the way to 4 feet. I kind of ran out of room here, so let's actually try to erase by, well, see there, there we go. Now I got it going. Okay. So let's try that again. We'll start at the top there, 4, 3, 2, 1, and 0. Okay, so suppose, what I do is I just say, well, we'll approximate, and we'll go from here to here. That's 1 foot, and we'll just go with the beginning weight, right? It weighed 50 pounds here. So the work done here is going to be that 50 times 1, because I just raised it up 50. Now, then from here to here, 1 to 2, well, now it actually just weighs 40, so let me use the 40, and so that is 40 times 1 foot. Then now it just weighs 30 by the time I get there, and that would be then 30 times 1 foot. And here it weighs 20. I go 1 foot, so that'd be 20 times 1 foot. I add all those together, and I get 50, 100, 140 foot-pounds. But you see, what we did was we were just taking, if I redraw this this way. 1, 2, 3, 4. And so I say that's H. And now up here, there's 50. And there's 10. And we draw that way, and we call this F of H. And that's 50 minus 10H. You see, what I did was I said, oh, well, let's let it be 50 for 1 foot. And so I took the value of 50 times that 1 foot, and then 40 times 1 foot. Hey, we know what we're doing. I'm just building an integral from a Riemann sum. And so we see that this is, yeah, how we build integrals. If I wanted to get a better estimate, right, go every half a foot, go every fourth of a foot, right? And so I'm just taking this F at some HI times my delta H, and I'm summing that up over all I, say I equals 0 to n, or n minus 1, or something like that. But I'm just doing that, and as I let my delta H go to 0, n go to infinity, I just have this integral from 0 to 4 of my f of h dh. And so in this case, this is integral from 0 to 4 of 50 minus h, oops, 10h, would make a difference, dh. And so this is the integral. Well, actually I can do that integral. So that's 50h minus 10h squared over 2 from 0 to 4. And so that is 50 times 4 minus 5 times 16, and then minus 0. So this is 200 minus 80, and we get 120 foot-pounds. So there you go. That's the work. The big question is going to be, how does the force change over the distance? Because the distance maybe, really isn't changing, right? I mean, I go this distance, whatever it is, but the force for each distance could change. So that is what we're doing, and we'll take a look at some more problems.